Hello everyone, my name is Zhang from KAIST. Today I will talk about our work, which is revamping storage class memory with hardware automated memory over storage solution. Firstly, I will use a single slide to summarize this presentation. Nowadays, there's a huge demand for increasing the memory capacity to execute larger-scale data-intensive application. Unfortunately, DRAM DIMM or NVDIMM has only 2 to 64 GB memory capacity. We can use a Linux MMF module to expand the memory space with SSD. However, this software approach can introduce significant software overhead. Its performance is limited by the physical hardware boundaries and cannot guarantee the data persistency. We propose HAMS, which is a hardware automation approach to expand the memory space with ULL-Flash. HAMS unify the traditional memory space and the storage space as a single memory pool. This memory pool can achieve a terabyte scale memory over storage space, and our hardware automation scheme is transparent to the operating system. So HAMS can fully eliminate the software overhead, break the hardware boundaries, and guarantee the data persistency. Our evaluation results show that HAMS can offer over 2 times higher system performance compared to the MMF-based system. It also can guarantee low energy cost compared to the MMF-based system. I will start the presentation with motivation. Nowadays, there emerges a lot of larger-scale applications such as scientific computing, artificial intelligence, and big data analysis. Such applications usually consume a huge amount of execution time and demand a powerful hardware platform for the computation acceleration. To satisfy the requirement of the application, high-performance computing, such as Fukaku HPC, have integrated more and more computing nodes in the memory capacity. The Fukaku HPC employs 159K nodes and 4.585 petabyte DRAM. They can deliver 975 petaflops computing power. The computing power of supercomputers is increasing exponentially by employing more and more computing nodes. From the Edison in 2015 to Corey in 2016, the computing power has increased by a factor of 10 in a year. The scalability of the memory capacity actually falls behind of the increasing computing power. For example, the overall memory capacity in Corey is only increased by 2.5 times, from 356 terabytes to 875 terabytes. Normally, the most reasonable ratio of the memory to the computing power is 0.5 byte per flops. But for Corey, this ratio has reduced to 0.03, which is much lower than the standard. We can spend more money to expand the memory capacity. For example, with Corey, we can install 13.5 petabyte memory. However, this will lead to another problem. Too much memory can consume too much energy. For example, the power consumption of 13.5 petabyte memory exceeds the limits of the Corey system power consumption. Due to the limited capacity and huge power consumption, the existing DRAM-based memory system cannot satisfy the data-intensive application in their large-scale dataset. We expect a future memory system can replace the existing DRAM. The new memory should provide large capacity with scalability. It should deliver the performance similar to the DRAM. It is non-volatile to store data persistently, and it also should consume low power. In fact, there already exist multiple future memory research, but they all face a lot of challenges. One potential type of future memory is NVDIMM. It integrates a small piece of flash as a backup storage and employs a supercapacitor as a battery. When there is a power failure, the NVDIMM controller will flush the data from the DRAM to the flash, which can make the data persistent. As only DRAM is used as a working memory, it can achieve high performance. As flash is used to backup data, NVDIMM is also non-volatile. However, flash is not used for the memory expansion, so NVDIMM's capacity is limited. It also cannot mitigate the power consumption of the DRAM. NVDIMM is another good candidate to be a future memory. NVDIMM replaces the DRAM with a storage class memory, such as the 3 course point and the PRAM. The emerging non-volatile memory can provide scalable capacity by stacking multiple planar layers of the cells. It is also non-volatile and consumes lower power. However, the storage class memory performs much worse than the traditional DRAM. For example, the Optane DC-PMM, which is a type of NVDIMM, it degrades the performance by up to 6 times compared to the DRAM. To address this challenge, the memory vendors such as Samsung, they integrate the DRAM into the NVDIMM to accelerate the memory access. This new architecture can achieve high performance and relatively low power. However, the existence of the DRAM makes the NVDIMM volatile, and the overall capacity of the NVDIMM is not scalable. The technique shift in the NAND flash brings a new hardware solution to build the future memory. The ultra-low latency SSD, also known as the ULL-Flash, has been available in the public domain. The ULL-Flash is a new type of SSD which is built from the high-performance flash memory. The figure in the slide shows the performance comparison between the traditional NVMe SSD and the ULL-Flash in terms of the I/O latency. Compared to the NVMe SSD, ULL-Flash reduced the latency by 95%. But we still cannot directly replace the DRAM with the ULL-Flash. There are two reasons. Firstly, the ULL-Flash is a block device. Its access granularity is a page, so CPU cannot access ULL-Flash directly through the load and store instructions. Secondly, the ULL-Flash costs 3 microseconds latency to access a single page. It is much longer than DRAM, which costs only 100 nanoseconds to access the cache line. In fact, the Linux provides the memory mapped I/O file MMF to fuse the DRAM and SSD for the memory expansion. With this technique, the application does not care if the data exists in the memory or in the SSD. It can access data with load and store operations. MMF does not allow the CPU to directly access data from the SSD through the load and store instruction. Instead, the operating system will bring the target data from the SSD to the memory and then let the CPU access the data from the memory. So the operating system also needs to dynamically schedule what data should go into the memory and what data need to be moved out of the SSD. This software approach can leverage the ULL-Flash to increase the memory capacity. It saves the power consumption by maintaining a relatively small memory capacity. However, this approach still suffers from the performance issues and the data persistency issues. The left figure shows the performance difference of the different MMF-based systems, which employ the SATA SSD, NVMe SSD, and the ULL-Flash. As you can see from the left figure, the ULL-Flash can significantly increase the overall performance compared to the SATA SSD and NVMe SSD. The right figure shows the execution time breakdown. I split the execution time into the CPU time which is consumed by the user application, the SSD response time, and the time consumed by the storage stack. As you can see from the figure, the storage stack becomes the dominant factor that impacts the MM-based system. The storage stack overhead includes the time consumed by the page fault handling, multiple system calls, the latency of TLB misses, the page table entry reconstruction overheads, and the multiple context switch. Here I will show the details of the storage stack overhead. When the MMF is activated by the user application, the operating system needs to link a file to the virtual memory areas. Once the virtual memory area is created, the user process can issue load and store instruction to access the target data by referring to the virtual address. But the virtual address needs to be translated by the memory management unit to find out the physical memory location. If the data does not exist in the page frame, MMU invokes the page fault and the context switch occurs. The OS will allocate the free page from the free page pool to accommodate the target data and issue an I/O request to the storage. But as the data is stored as a file in the storage, accessing the target data needs to go through multiple software layers, such as virtual file system, block MQ layer, NVMe driver, and the flash translation layer within the SSD. These layers perform multiple address translation and request queuing. This procedure also takes context switch and the response to I/O interrupts. All these steps should be taken to serve a single page, so the overhead of the MMF cannot be ignored. The MMF approach also faces the data persistency issue. Although the ULL-Flash stores the data persistently, the traditional DRAM is a volatile memory. which can be vulnerable to the power failures. The I/O transaction also can be atomic and consistent. However, it requires extra protection from the software stack, including the MMF and the file system. We provide a new design of the future memory. It is called HAMS, which is Hardware Automated Memory Over Storage Solution. Our HAM is a solution to resolve the performance and the persistency issue of the traditional MMF-based approach. Specifically, as you can see from the right figure, we employ the NVDIMM as an inclusive cache. The NVDIMM is non-volatile, which can address the weakness of the traditional DRAM. We also employ the ULL-Flash as a memory backends. To eliminate the OS software overhead, we automate the data management between the NVDIMM and the ULL-Flash in hardware. The hardware design is called HAMS or controller. We also design a new hardware approach to build up the NVDIMM and the ULL-Flash as a uniform persistent memory space. As mentioned before, we replace the traditional DRAM with NVDIMM. In traditional computer system, DRAM communicates with the memory controller and the ULL-Flash communicates with the PCI root complex. Owing to the different data paths and the different controller, NVDIMM cannot communicate with ULL-Flash directly without the assistance of the CPU. We propose our HAMS controller, a uniform controller to manage the memory controller and the PCI root complex. Within the HAMS controller, a memory controller connects to the NVDIMM. This is the same as a traditional memory controller hub. On the other hand, we employ a new NVMe engine to interact with the underlying ULL-Flash. The NVMe engine is a simplified hardware implementation of the traditional NVMe driver. We also design an address manager to arbitrate the memory request to access either the NVDIMM or the ULL-Flash based on the tag array. If the incoming memory request hit in the tag array, it indicates the target data received in the NVDIMM. The NVDIMM will directly serve the memory request. Otherwise, the address manager will fetch the data from the ULL-Flash and move the data to the NVDIMM. We use a DMA to enable direct data transfer between the ULL-Flash and NVDIMM. Once the data is ready, MMU is invoked to re-access data from the NVDIMM. Next, I will talk more about the internal of the address manager. We explore different design space for the address manager. Firstly, we decide not to directly integrate the address manager in the MMU. This is because the data is dynamically migrated between the NVDIMM and the ULL-Flash. However, updating the page address in the MMU will introduce huge software overhead. So we also do not consider to use a pseudo LRU page replacement scheme, which is normally used in the Linux kernel. This is because the pseudo LRU can introduce hardware overhead and the memory space overhead to store the metadata. In our designs, we use the tag array as a key component to identify if data exists in the NVDIMM. Our design is simple and our goal is to achieve near zero overhead. For simplicity, we construct NVDIMM as a direct map cache. We also integrate the tag into the data array to eliminate the storage overhead. Here is a figure to show the design details. The tag of 64-byte data can be integrated into its ECC region. When a memory request arrives in the address manager, the address manager will refer to the index of the memory request to fetch the data from the NVDIMM. The data and the corresponding tag will be accessed together. If the memory request hits the tag, the fetched data will serve the memory request directly. Next, I will talk about our implementation to enable persistent memory system. NVDIMM and ULL-Flash are persistent memory, but I/O transactions without MMF and the file system supports are not persistent. There are several challenges. Firstly, the metadata of NVMe engine is vulnerable to the overrides of the user application or operating system. To address this challenge, we allocate the memory region to store the metadata. This memory region is invisible to the MMU. In addition, this region will be used by the NVMe engine to store the metadata of the I/O transactions. So we decide to pin the region to the NVDIMM. The metadata of the NVMe engine includes the NVMe submission queue, completion queue, PIP pool, and the MSI table. One concern regarding to this design is its storage overhead. As NVDIMM capacity is small, the capacity of the pinned memory space is also limited. However, according to the NVMe protocol, CPU can create up to 64K queues, and each queue can contain up to 64K entries. Managing these large numbers of queues in hardware is not easy. We make an experiment. The figure you can see from the slide shows how the I/O queue depth can impact the performance of ULL-Flash. As you can see from the figure, the bandwidth of ULL-Flash saturates at around 16 I/O queue depths. This result means that we can reduce the number of NVMe queues and entries in the NVMe queue engine without sacrificing the ULL-Flash performance. Another challenge is that the NVMe queue engine is vulnerable to power failure. Here's the examples. Let's suppose the NVMe queue engine sends 3 NVMe commands to the underlying ULL-Flash. ULL-Flash has complete commands 1 and 3. It is processing command 2. If there's power failures, command 2 is lost. One potential solution is to tag the fuel in each IO request. NVMe queue engine will send IO requests one by one, but this design will ruin the presence of the NVMe protocol. We propose a new data structure called journal tag. One on-the-fly command will be set to 1, and the one finished command will be set to 0. In this example, only command 2 is set to 1. When there's power failures, NVMe queue engine detects command 2 is incomplete by just going over the journal tag. As the NVMe submission queue is stored in the NVDIMM, so we can easily fetch the original values of the command 2. We allocate a new submission queue and completion queue after the system reboots. The new queues are used to reissue the command 2. We also ring the doorbell registers in the NVMe controller to inform ULL-Flash of the new command. The baseline of the HAMS is suboptimal to the data migration and the redundant data copies. One issue is that as the NVDIMM uses a memory-specific DDR interface and the ULL-Flash uses a PCI interface, data transfer between the memory and the SSD always need to be routed by the proposed address manager. Another issue is that the SSD usually employs a small piece of DRAM as its internal cache. In my design, the cache inside the SSD will become the secondary cache between the NVDIMM and the ULL-Flash backbone. But the SSD internal cache has much lower capacity than the NVDIMM, so this means that the internal cache within the ULL-Flash is not useful. We optimize the baseline solution called aggressive HAMS. Firstly, we unify the interface between the memory and SSD. To achieve this, we design a flash-based DIMMs, so memory and SSD can share the same hardware facility such as DDR5. When migrating data between NVDIMM and SSD, the address manager will only control the instruction and address. SSD can directly access the target data from the NVDIMM without the assistance of the address manager. On the other hand, we eliminate the SSD internal cache, and the SSD controller can directly read and write instruction and the data from the memory. Next is the evaluation of HAMS. We set up our experiment based on a full system simulator. We module one 8GB NVDIMM and one 800GB ULL-Flash in the simulator. We also set up 10 different NVDIMM systems. MMAP is an MMF-based computing system. We set up 4 different HAMS systems based on the baseline and aggressive HAMS. We also use the fewer and our new design to enable data persistency. We compare 5 different prior work. Flat Flash enables the CPU to directly access ULL-Flash through the MMIO with or without using the DRAM as cache. NVDIMM-C uses the TRFC to enable the NVDIMM and the Flash communication. Optane uses the Optane DCPMM with or without using the DRAM as cache. Next, I will show the overall performance of different systems. Firstly, I compare the MMF and our HAMS. Our approach can improve the performance by 154% and 148%. We also compare the prior work which guarantee the data persistency. Our approach can improve the performance by more than 40%. We also compare the prior work, which optimizes the performance but cannot guarantee the data persistency. HAMS can achieve similar or even better performance than the prior work. We compare the execution time breakdown and energy consumption. HAMS can save the 58% user-level execution time. This is because HAMS fully eliminates the software overhead. HAMS also reduces the CPU interventions. So HAMS achieve 45% energy saving. I also show the time series analysis of executing a single user application. As you can see from the figure, during the application code launch, HAMS takes shorter times to reach the stable performance compared to the MMF. During the long-term execution, HAMS also delivers higher performance than the MMF-based system. Thank you for watching this video.